Yo, what's up, Calculus? It's Mr. Laverd's class, back with another episode of Section 311, Hyperbolic Functions. I'm just as excited as you are, so without further ado, let's get right into the blog.
Hey guys. All right, I'm turning off this. All right, how do I get this? Okay. So the first thing that I wanted to do is talk through the kind of the rundown of the schedule. Okay, what we're doing each day. Now we don't have to get right into notes today. I was going to leave it. I can answer questions about Section 310. I can answer anything from the homework from Section 310 if you'd like me to, or we could get right into Section 311. So today, Tuesday, we've got questions, and then as much as we can get done out of Section 311. Okay. I'm not going to lie to you. Section 311 is pretty difficult. In my opinion, it's just weird. It's just something you've never seen before. We'll talk about it a little bit later. But so we're definitely going to have to do some of Section 311 tomorrow. Okay. And then on Thursday, I'm just going to plan on it right now. We're going to have a work day over the Section 311 assignment. Okay? Because I want there to be a day where you can ask me questions over some of the stuff. So that's Thursday. Now, on Friday, we're going to start reviewing for our Chapter 3 test. Review Chapter 3. Okay? On Monday, same. Okay? Now, I'm going to kind of leave it open. We have kind of a little bit of wiggle room. We could either, if we feel comfortable enough with it, we could either have our test Tuesday and Wednesday. That is the Home Alone music. I would know that music too. We could either have our test Tuesday or Wednesday, or if we wanted to push it back, we could do our test Wednesday, Thursday. Here's the deal though. Every day that we push it back is a day less of review for our exam. Okay? Which is, so we will start doing exam review Monday, Tuesday, Wednesday. So, and then our math exams are going to be next Thursday, Friday. Okay? So Thursday, Friday of, no, this is next week. And then the following, the 17th and 18th.
Okay, because I was like, wait.
No. Yeah, the 17th and 18th, that's when our exams are. Okay? So we could either spend, we would have 5 full days of review. Obviously, one of those days is going to be a work day over the exam review. And then we'll just start to go over problems and just kind of go over the entire thing before our exam on Thursday, Friday. It just kind of depends on what we'd like to do. If we feel like we need another review day in between before our Chapter 3 test, we could do that. That just bumps that back to test Wednesday, Thursday, and then we would have Friday, Monday, Tuesday, Wednesday to review for our exam before we take it. Yeah.
So is every exam Thursday, Friday?
No. So they changed the exam schedule. The main reason they changed the exam schedule is because if you think about the exam schedule, everybody would eat lunch at the exact same time. Everybody. And they obviously can't do that this year.
Why not?
Because.
No.
Because there's assigned seating and it's just a mess. So what they decided to do was on Tuesday and Wednesday, half of the classes are going to give exams. On Thursday, Friday, the other half of the classes are going to give exams. And it's all by subject area.
So that Thursday, Friday, we won't have those classes.
No, you'll still go to those classes. I don't know what they are. Like your English classes, like I would really hate to be the classes that give exams on Tuesday, Wednesday. Because like, what are you really going to productively do on Thursday and Friday? Honestly, I hope they give you time to study. That way you can study for your other exams. like, I really don't want to give you guys too much work to do on Tuesday and Wednesday of that exam week, because I feel like that's mean to your English teachers. Like, I'm giving you work to do where you should be studying for your English exam. You know what I mean? So, I don't know. And I really hope they don't try to give you assignments to do on Thursday, Friday, because I would hope that you would be reviewing for your math exam. But at any rate, exam week is this last week, the Monday is normal. Monday's a normal day. Tuesday, Wednesday, Thursday, Friday are the exam times. But your math exams, I know English, I'm not exactly sure the rest of the breakdown, but I know English is the Tuesday, Wednesday, math is the Thursday, Friday. It is? I feel like foreign languages is on a Thursday, Friday as well. Now, again, what we're going to do is break it up in between the two class periods. So, I mean, for a block scheduled exam day, you would get an hour and a half anyway. So, I mean, it breaks it down. You actually get a little bit more time doing this schedule, but you know, obviously there's time to come in, sit down, attendance, and all that junk. So.
There's like more time, but also like not.
Right, more time, but not. Right, and just pray that I have no idea what they're going to do. I have no idea what you mean. No idea. Yeah.
Are we doing a calculator, no calculator? Or is it...
I don't think there's enough no calculator stuff for me to try to do a no calculator portion. I know, it would just be a very limited amount of questions.
Just
And
pull your
it's
calculator.
at that point, why would I do that? That's silly. So I'm guessing that it would just be full calculator. Yeah.
Are you gonna do it to where like we have one part one day and then start the next part, or are we just gonna do?
I think I'm just gonna try to do one part one day, one part the next. Okay. Like we've been doing the test. Yeah. Okay, questions? Anything else about the schedule? Okay, so let me ask you this. What questions do we have over the section 310 assignment? I hear 15. Chapter 3. Oh, had it. There it was. Oh, no. I got it. Darn it. Okay. I'll do all of it. Okay. I like top number 15. Good one. Did it go? Are you going? Hello? There it goes. Okay. So let's talk through number 15. Now, it says find the differential, right? Remember the differential equation was dy is equal to f prime dx, right? That was the differential equation. The difference in the y's per difference is equal to the derivative at that point times the differential in the x. So it says that for number 15, y is equal to e to the x, e to the x over 10, where x is 0 and dx is 0.1. So what is this telling me? This is telling me at 0.0 comma something, that's where I'm taking the differential. At 0.0 comma something, and I don't even need to know what that y value is. 0.0 comma something, and the differential on x is 0.1. So meaning, like for my x values, I'm going from 0 to 0.1, right? I'm finding dy from 0 to 0.1. Okay, so dy is equal to f prime x. Now, think about this. This is, excuse me, e to the x over 10. This is a chain rule, right? This is a chain rule. So this would be e to the x over 10 is just e to the x over 10 times. Now, if it's x over 10, that's like 1/10 x, right? 1/10 x. So if I differentiated 1/10 x, it would just be 1/10 and then times dx. Right? That's a chain rule. That's why I'm multiplying by 1/10, because it's a chain rule. I differentiate e, and it's just e to the x over 10. And then I differentiate x over 10, which is just 1/10 x, so it's just 1/10. The x will go away, just become a constant.
That's like that's not y. No,
This?
no, the other one. Isn't it e to the x over 10? Isn't that coming from y?
Yeah. But that you're just taking the derivative of that thing. Whatever the function is.
I thought it was going to the next problem.
Oh, no. We're only doing, 15. Okay, so what does that mean? That means that I want to find dy. So this is my true differential, right? That was my answer to part A. Part B says evaluate dy given the values of x. So dy is equal to e to the 0 over 10 times 1/10 of 1/10. Okay. So dy is equal to, well, that would be like e to the 0, or just 1, times 1/10 of 1/10. So 0.1 times 0.1, which is 0.01. So dy is 0.01. Now, what is that telling me? Try to interpret your results there. That means that between when I vary x with 0.1, right? When I make the differential on x as 0.1, at 0.0, right? At the value of x equals 0, the differential within the y's, if I let my x vary by 0.1, the differential within the y's will be 0.01. Okay, what other questions? Yeah. 23. Linear approximation or differentials. I think I use differentials in the key. I just think that's easier. Let me pull out the actual key real quick. Oh, it's already in the binder. I want to do it the exact same way. All right, this is problem number 23. Oh, I know, I did linear approximation. Oh, what was I thinking? Okay, remember, linear approximation, we're doing, whoa, that's not a pen. We're doing 23. Linear approximation is L of x is equal to f of a plus f prime of a times x minus a. Okay, so now we just have to figure out what these things are. Well, if I've got 1.999 to the fourth power, that's like saying it's x to the fourth power, where x is 2, because it's really close to 2, right? And the difference in the x, the delta x, the change in x is 0.001, right? Because it varies away from 2 by 0.001. Okay, so that means L of x is equal to f of a. So a is my 2 value. Okay. So it's 2 to the fourth plus f prime of a. Well, x to the fourth turns into 4x to the third. So f prime of a is 4 times 8, right? Or I guess I could just write 32. And then I multiply that by my x minus a. Now remember, x minus a is your difference in the x value, right? It's like saying 2 to 1.999, right? 2 minus 1.999, or 1.999 minus 2. but it's really, the difference is the 0.001. That's why I listed this off too. All right, now I take this and I take 2 to the 4th plus 32 times 0.001. 16.032. Oh, I messed up something. Look. Take a look at this. The difference in the x boop, 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 is actually down 0.001. Whoops. I know. Yeah, because it's x minus a. X is 2. So I really take 1.99999 minus, or sorry, 2, excuse me, 1.999 minus 2. So it should be going down 0.001. Whoops. Sorry, folks. Insert a negative. That's my answer. 15.968. 15.968. That's my answer. You know, in this case, would have been easier just to calculate that value. It should always get you very close. Very close. Because what you're doing, again, when you're doing a linear approximation, you're just getting it. It's close enough for what you're looking at. There's the linear approximation that guys. What other questions do we have? Anything else we want to talk through? I'll post a key, but then you can still ask me questions once we start reviewing. I mean, I'll open it up for questions on any of the sections. Yes.
So delta x is just the x minus a.
Yeah, the change in x. Change between the two
And
values.
then you probably answered this like in other videos, but so when you're going from like 1.99, is it always to the next greatest whole number?
Well, we just you kind of like estimate it to where you think it's close enough to.
So then is A like the approximation, like the value of approximation?
Yeah. Yeah.
Being number 5.
5. Cinco. Are you here? All right, find the linear approximation of the function at a equals 0 and use it to approximate the numbers 0.9 and 0.99. I'll just do the first part here, and then obviously you could just graph it on your graphing calculator to show the tangent line. Kind of like what we did in class too, where the tangent line was right above it, and that you see. All right, so take a look here. I've got 1 minus x, square root of 1 minus x, excuse me. And the linear approximation is always L of x is equal to, what was it? It was f of, I have to remember. Just wrote it. F of a plus f prime of a times x minus a. F of a plus f prime of a times x minus a. I don't know why I needed to remember that. That's just always our equation, right? It's the slope, that times x minus a, that slope is the f prime of a. So it's f of a times this plus the slope times x minus a. All right, so f of a, well, I plug in, it would be the square root of 1 minus 0. So it's the square root of 1, or just 1. And then I say f prime of a, okay, so square root of 1 minus x. If I find the derivative of that, remember that's like saying 1 minus x to the 1/2. So that's equivalent to saying 1/2 1 minus x to the negative 1/2. And then since this is a function within a function, I've got to use chain rule. I've got to differentiate the 1 minus x. But in this case, it just is multiplied by a negative 1. Why a negative 1? Because 1 minus x, if I differentiate that, the 1 goes away, but the minus x just leaves a negative 1. That's a times. times. Okay, so this is, again, I think it might be easier to do this. 2 radical 1 minus x. 1 minus x, and then times -1. So let's put a -1 on top. So that's the derivative there. So let's plug in 0. So f prime of a would be -1, 2 times radical 1. So it's -1/2. So times -1/2 times x minus a. Well, times x, because a is 0. Okay, so that means L of x is equal to 1 plus, and I'm sure we can change that into a minus 1/2 x. That's my linear approximation. 1 minus 1/2 x. That's the straight line at 0 that lies tangent to square root of 1 minus x.
I think it's square root of 1 for A.
It's f of a. A is 0. So if I plug 0 into there, it'd be like 1 minus 0. All right, now it says use it to approximate 0.9 and 0.99. Well, that now means, excuse me, my x, if I've got the square root of 0.9, I got to figure out what my x is, right? Got to figure out what my x is to approximate that x, or to approximate using linear approximation. So my square roots go away. I got 0.9 is equal to 1 minus x. I subtract over, so that means I've got a 0.1, and then I've got a negative there, so it's a 0.1 as my x, right? So that would mean L of 0.1 gives me 1 minus 1/2 of 0.1, and it looks like in the sheet here, 1 minus 0.05, 0.95. And then I want to do the same thing for 0.99. Square root of 0.99. So solving for x there, I would get square roots go away. Subtract over 0.01 is x instead of 0.1. And so that means L of 0.01 is going to be 1 minus 1/2 of 0.01, which is 0.995. Right, 0.995, yep. That make sense? All right. Can we get into a little bit of section 311? Okay. Let me preface this section by saying, I think it's ridiculous that you guys have to learn. I think you guys have to learn this. I know, that's a really good intro, right? That's like I should probably like turn off the video so that I can dash it. Because I gave the supervising teacher that I have from Stark State, because they're not allowed to like come into the school and like do formal observations. Like I gave them access to my campus, so they can watch any video at any time. So there might be seeing you doing your little like they do stuff. But at any rate, I don't think even I have to check back in my calculus. I don't think I ever learned this section. I think we skipped this section when I was in college. We can skip it too. No, but we can't. That's the problem. I'm bound to teaching the great curriculum that is set forth by Stark State and these awesome professors there. Now here's the deal. I wouldn't say that this is, I don't know. I said it was difficult. I don't know if it's difficult. It's just weird. It's just weird. What I'm handing out to you right now is a formula sheet. This is just for you guys to look over, to have. When I was doing the homework, I kept having to flip through in the notes and like, find everything. within the notes, so I just kind of made this just for reference.
I don't know, a lot of letters or something.
Yes. Yes.
Why is that when you get older, you get more letters?
There's more letters than numbers in math. I know. I know. Okay. Gosh. Gosh.
What's the cost of that?
And I like
Hand.
cough.
Where did this even come?
Okay, so what the heck is this thing? You know, it was funny. I was on Thursday. I was watching a video of because I have a YouTube channel with the teacher at Jackson, and she's already taught this lesson. So I just kind of like watched her teach it just to see what she said at certain parts, and honestly how deep, because you could like dive deep down the rabbit hole with this stuff. And so just kind of watching to see how deep she dove. Yeah, that's what he said. And she was explaining to her students like it's kind of, this is something that unless you are like going to be an engineering major, like you may never ever use this ever again. Yeah.
Why would I use this?
Right. So what are hyperbolic functions? Well, what we have here are sine, cosine, and tangent. Original sine, cosine, and tangent were based off of a right triangle. Correct? They were based off of a right triangle. And they had certain properties, certain values of sine, cosine, and tangent related to a circle. Right? They related to this unit circle thing where we could easily find the sine, cosine, and tangent values and then relate that to the secant, cosecant, and cotangent values of pretty much anything that we really wanted to find. Right? Similarly to the way that that sine, cosine, and tangent fit to a circle, we have these things called hyperbolic sine, cosine, and tangent that fit to a hyperbola. Okay. Now, what is a hyperbola? Remember, a hyperbola is like a 1 over x, right? It's the thing that it's got two tails to it. And let me show you some of the graphs of these things so I can show you. But we have these things, and this is what these are defined to be. Okay. I don't want to dive deep enough to tell you exactly how you get these things. I'll kind of show you on the graph how they relate to e to the x, why you see so many e to the x's going on. But these are how we define sine, cosine, and tangent in terms of e, basically. Sine, now this is how we know that we're talking about hyperbolic sine rather than regular sine. And hyperbolic cosine, it's that h right after it. Okay? So sine h, hyperbolic sine, is equal to e to the x minus e to the negative x divided by 2. E to the x minus e to the negative x divided by 2. Cosine hyperbolic of x is e to the x plus e to the negative x divided by 2. So notice how sine and cosine relate really closely to one another. Right? Gone are the days where sine is just opposite over hypotenuse, related directly to a right triangle. These are relating directly to a hyperbola. Tangent is still sine over cosine. Hyperbolic tangent is still hyperbolic sine over hyperbolic cosine. And the cosecant, secant, and cotangent are the same reciprocal. So cosecant hyperbolic is 1 over sine, hyperbolic sine. Hyperbolic secant is 1 over hyperbolic cosine. And then cotangent, hyperbolic cotangent is just the reciprocal of tangent, right? So hyperbolic cosine over hyperbolic sine. Okay. Let me show you the graphs of these things. Take a look, and I'm going to move left to right here. Take a look at the blue line on top. This is 1/2 e to the x. Right? This is 1/2 e to the x. This is negative 1/2 e to the negative x. See, what we've got here are these two tails, right? What we have are the two tails, and that's basically a hyperbola, right? These two tails happening at the same time. So what we're looking at here is sine, hyperbolic sine is going to fit directly in between them. Okay, it's going to be exactly in between them. I've got 1/2 e to the x and negative 1/2 e to the negative x. Right? Negative being we flip it downward. Basically, the negative and the negative mean that they're a reflection of both over the x and y axis. Right? So if sine is directly in between them, basically if I wanted to find the average of the two, I would just add these two together. And that's really, look, 1/2 e to the x, negative 1/2 e to the negative x. If I add those two things together, I'm basically getting e to the x minus e to the negative x all over 2. So it's basically the direct center of those two values. Take a look at hyperbolic cosine. Hyperbolic cosine, I've got 1/2 e to the negative x and 1/2 e to the positive x. If I add those two things together, I'm going to get e to the x plus e to the negative x, all divided by 2. If I added these two equations together. Now, tangent is just a weird thing all on its own. You kind of saw that in pre-calc. You know, tangent really has, it doesn't wave like sine or cosine does. It's kind of like this weird thing that happens all by itself, right? That's the same thing for hyperbolic tangent too. Hyperbolic sine and hyperbolic cosine, I can show you, and you can kind of see where we get the equations, but tangent, okay. They're just weird tangents. There are many applications. Okay, there are many applications within engineering, many applications within physics, within a lot of different applications. Basically, they introduced this section with saying, we're going to introduce this to you right now, and then we're going to finish it off in chapter 7 and chapter 11. We get to chapter 6. Okay, so like we never even get to there. If you continue on, you know, perchance you use this book in college too, because a lot of college calculuses use this exact same book that we're using right now. If you continue on and you end up doing this, well then you got a base knowledge of it, and you can kind of understand what's happening based on what we're doing in here. What we're going to be working a lot with is hyperbolic identities. Remember doing trig identities in pre-calc? We're doing the exact same thing here. But now we have a new set of identities. Okay? Now we have a new set of identities. We have the hyperbolic identities. Here's just some of them. And that's why I give you the formula sheet. Because they're weird. They're not like your pre-calc trig identities. They're not like the identities that I gave you, you know, on Mr. Delap's cheat sheet. Right? Not that I don't have any more copies of over there. Okay? So here's, yes.
We have to memorize these.
I'll tell you in a minute. That's what I thought.
Yeah, we're good questions.
So hyperbolic sine of negative x is negative sine, and you will actually prove some of these. We'll prove some of these in class today, and then you'll prove some of these later on in your homework. So prove that basically sine, hyperbolic sine of negative x is negative hyperbolic sine of x. We're going to show that hyperbolic cosine of negative x is actually just cosine, hyperbolic cosine of positive x. Remember how it was sine squared? What was the trig identity with sine squared and cosine squared? Sine squared plus cosine squared is 1, right? Remember that? Take a look at the hyperbolic. It's just weird. There's just something off about it. It's like some alternate dimension. Cosine squared of x, and this is hyperbolic. Hyperbolic cosine squared of x minus hyperbolic sine of squared of x is 1. So it's flipped, and it's subtracted instead of added. Okay. We can say 1 minus hyperbolic tangent squared of x is secant. We'll actually, I think we do this in the homework, one of the two, I can't remember which one. Hyperbolic sine of x plus y is equal to sine x cosine y, cosine x sine y. And that is actually one of the trig identities that looks to remain the same. There's one of them where the angle sum ones, I think actually is the same identity. Sine, cosine, cosine, sine. So we got basically these new sets of identities here. So let's do this one. This might be the only one we do today. Prove that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. And that's one of the identities that I showed you on the last slide. We're going to prove that fact. And then we're going to prove 1 minus hyperbolic tangent squared of x is equal to secant, hyperbolic secant squared of x. Okay, so remember, back in pre-calc world, proving trig identities, you basically chip away at one side of the equation to try to get to the other side, right? You keep kind of just throwing stuff at the wall and see what sticks and just try to make it to the other side. Sometimes it's easier to kind of chip away at both sides and try to make them equal out so that you can kind of almost work backward. But for our purposes here, for problem A at least, and for problem B, it's just easier to chip away at the left side. All right, so I'm going to go straight away and actually just show what hyperbolic cosine and hyperbolic sine is. Remember, because this is the same thing. Cosine of x squared minus sine squared, right? Okay, so let's, you know what, I'm going to get one more sheet of my own. There we go. So let's plug in. Hyperbolic cosine of x is e to the x plus e to the negative x over 2 squared minus hyperbolic sine. Oh, shoot. No, I had that right. Sorry. E to the x minus e to the negative x over 2 squared. All I did was just plug in what they equal. Okay, and now let's distribute the squareds everywhere. Let's do a little side work. E to the x minus e to the negative x. Oh, let's do the plus first. Squared is like saying this, e to the x plus e to the negative x, right? Don't forget that we can't just distribute the squared all the way in. We got to FOIL the numerators here. So foiling the numerators, e to the x times e to the x is e to the 2x. And then I have e to the negative 2x, because it's e to the x times e to the negative x. So it's plus e to the negative 2x plus e to the negative 2x. Oh, wait. No, that's not true. That's not true. Sorry. Back up. Excuse me. If I've got e to the x times e to the negative x, what happens there? I did that when I was starting this problem, when I was doing it. The x's cancel in the exponent, don't they? Makes it 1. Because if I want to multiply the bases, I add the exponents. So this would be e to the x plus negative x, or e to the 0, which is just 1. So we actually get plus 1 for our firsts, or for my outers, e to the x times e to the negative x. And coincidentally, or not so coincidentally, that happens again for my inners, e to the negative x times e to the positive x. And then my last is that plus e to the negative 2x. That one's the plus e to the negative. All right, so the numerator here is e to the x plus 2, e to the 2x plus 2 plus e to the negative 2x. All over 4. And I'm going to say minus, I'm going to use parentheses here. I know it's going to be something over 4. But let's go ahead and FOIL this one. It's going to be very similar. E to the x minus e to the negative x times e to the x minus e to the negative x. Okay, so this gets me e to the 2x, my firsts. My outers and inners. Okay, in this case, excuse me. In this case, it's just going to be a minus 1 and a minus 1. Because it's negative e to the negative x times e to the x. So it'd be a minus 1 instead of a plus 1 like we had before. And then a plus e to the negative 2x. Negative e to the negative x times negative e to the negative x is positive e to the negative 2x. So this gets me e to the 2x minus 2 plus e to the negative 2x. Okay? And now we simplify because I've got common denominators. It's something over 4. Right? E to the 2x minus e to the 2x. Those will cancel. Again, we got a minus sign in between. We've got e to the negative 2x plus e to the negative 2x, or minus e to the negative 2x. Those will cancel as well. And then we've got 2 minus a negative 2. So we end up getting a 4, which is 1. Okay, she can. We'll pick that up again tomorrow. Can't turn the video back on, so you can't be out. So long, everybody.